Hello, my name is Adam Boss, and this is my Physics 2212 Lab 5 Faraday's Law. The purpose of this experiment was to collect observational data of a magnet falling through a conductive tube of aluminum foil. Additionally, the purpose of this lab was to model this magnet and tube interaction computationally and thus compare the computational models with the observed data. The results from the experiment found that the length of the tube was 0.03 meters with the radius being 0.01 meter. The real time calculated, the average time was 1.21 seconds for the fall, while the code found a longer time, or a shorter time actually. For the formulas and methods, the most important fundamentals are the force on a wire, magnetic force on a wire carrying current, Faraday's law, which is of course a change in magnetic flux equal to the integral of the electric field or the EMF produced, the magnetic force on a magnetic dipole, as well as Newton's third and second law, and of course force due to gravity. So for the experiment, the north pole of the Bower magnet was to be found, and then the magnet was held vertically above the foil, which was also held vertically, with the north side of the Bower magnet held up, and the magnet was released. Then the time was recorded it took for the magnet to fall, and then after 5 times, the time was averaged for the magnet to enter and leave the tube. For the system included the magnet, and the surroundings was everything else, specifically the earth and the tube of aluminum foil. Now for the computational model, a lot of it included some given data, but the ones I specifically changed were, for example, the magnetic flux to be calculated between the ring and the magnet. Additionally, the total interactions between the two forces, specifically the force due to gravity and the force on the magnet due to the current, to find the net force on the magnet. Additionally, the magnetic field found on the ring was also calculated. And lastly, the force on the magnetic dipole was calculated using the code. So from the results of this experiment, it was found that the computational model was similar to the real-life result but faster due to possible errors. And the possible errors for this lab include air resistance, which explains why in real life it took a longer time for the magnet to reach the bottom because this component was not considered for the computational model. And this is a force of friction restricting against the motion of the magnet falling, which in turn means the time for the magnet to fall would be shorter in a computational model that is not considered for air resistance. Also, it is difficult to consider the magnet to be dropped perfectly symmetrical and vertical with the tube, which could have caused inconsistencies in the magnetic field and the force on the magnetic dipole. And there's also human error, which is dropping the magnet at inconsistent times and looking at the video and being able to decide when is the exact frame in which the magnet left. Other limitations in recording the data, of course, due to human error. And then for the what is of the lab, if there was no resistance on the aluminum foil, the current would infinitely get large because voltage is current times resistance, or voltage is current times resistance, so voltage divided by resistance is current. And with a zero resistance, the voltage is in theory, the resulting current would in theory be infinity, which means the magnet would drop even slower. And if there were holes in the tube, there would be an inconsistent amount of coils, or an inconsistent current going through all the coils throughout the aluminum foil, which would cause the magnet in turn to fall faster.